In this problem, I want to prove a formula for the Fibonacci sequence. We want to prove that you can access any Fibonacci number by this formula here. This formula actually has a special name. It's called Binet's formula. And it's based upon these roots, a and b, of this equation. The root a actually has a special name. It's called the golden ratio. B, I suppose you can call it the golden ratio's conjugate. Okay, so to do this proof, we're going to use induction. Now, in order to start off our induction, we'll need a statement. So our statement is that P sub n tells us that the Fibonacci sequence is solved with the given equation for n values, we'll say bigger than or equal to 1. Now, what we want to do is start off with a base case, and we're going to show that P sub 1 is true. So plug 1 in and see what happens. So F1 is indeed 1, so that checks out. And what about the formula? A to the power of 1 minus b to the power of 1 over top of a minus b, yeah, that's indeed 1. So our base case checks out. Now I'm going to try to just sketch what we're going to do next. Before formally completing the inductive step, I just want to make myself some space and set out a goal. What I want to do is show that Fn is equal to, now I'll leave some space before I get there, I want to get this equal to a to the power n minus b to the power n over a minus b. Now in order to do this, I get to use the fact that I could sub in smaller values of n. So I could use this for n minus 1. I could use this formula for n minus 2, and so on and so on and so on. I just have to come up with Fn equals the expression that I just wrote down on my page. So in order to do this, what I'm going to do is first apply the Fibonacci sequence. So our Fibonacci sequence says that Fn is the same as Fn minus 1 plus Fn minus 2. Now I'll apply Binet's formula, this formula that we're trying to prove, but for the smaller n values. So we would get a to the power n minus 1 minus b to the power n minus 1 over a minus b plus a to the power n minus 2 minus b to the power n minus 2 all over a minus b. Now if we take what we've written on the page and we try to factor together as much of the a's and the b's as we can, group them together and factor as much as we can, so we can factor out an a to the power n minus 2 with the a's, and what's left with the a? There's one a in the brackets and plus 1 for the a n minus 2 that came out. And for the b's, very similarly. So we can write b to the power n minus 2 and b plus 1 in the brackets. Now the question said that a and b are roots of a particular equation. They said in the question that a plus 1 is the same as a squared. So this means that what we've written down here gives us the result, right? Because we have a to the power n minus 2, and then the a plus 1 can be replaced with a squared. Similarly with the b plus 1 can be replaced with b squared. And this gives us exactly what we're looking for as a result in this question. Now, let's make this look a little bit more like induction. So our inductive step, what did we actually show in our inductive step? We showed that the statement P sub n minus 1 when grouped with the statement P sub n minus 2, so both of those together, we showed that they imply that P sub n is true. When it's true for n minus 1 and it's true for n minus 2, then it's also true for n. And we can do this for every n value bigger than or equal to 3. We're allowed to plug n's bigger than or equal to 3. And we've gone ahead and showed that in our inductive step. So if p sub n minus 1 is true and p sub n minus 2 is true, therefore p sub n is true. Okay, now we are not quite done yet. We got to go back to our base case. Why do we have to go back to our base case? Because we only showed one scenario. We also need to do this for f sub 2. F sub 2 is 1, and we need to verify the formula works for f sub 2. If we don't do this, our induction could fail. So a squared minus b squared over a minus b. Now let's remember, a squared is the same as a plus 1, and b squared is the same as b plus 1, so we have minus b minus 1, and again we have a minus b over a minus b, and again we get 1. So therefore the base case checks out, and in particular, therefore p sub 1 is true. And over here on the right hand side, we've shown, therefore p sub 2 is true. So this completes the induction. We could move on from here. I just want to talk about this process that we've just gone through a bit. The method that we used for this inductive argument actually has a special name. Most authors call this strong induction. It's a little bit different from the regular induction where you just look one step back. In strong induction, you could look 2 steps back or 3 steps back, or however many steps back you like. The two forms of proof are actually equivalent, meaning that if you can prove it one way, you could technically prove it the other way, but sometimes strong induction is a heck of a lot more convenient than just using the regular induction. Let's try to get some scrap space and play around with this idea a little bit. So let's sketch what's going on in regular induction. So in regular induction, we have all these statements. Let's say P1, P2, P3, P4, and so on and so on and so on. In the inductive step, what we're doing is doing all the hard work to show that the following implications are true. So 1 gives you 2. We show that that's true in the inductive step. We show that 2 gives you 3 in the inductive step. 3 gives you 4 in the inductive step, and so on and so on and so on. We show that all of those implications are true. Now that doesn't actually show that any of the statements themselves are true. That's actually what we do in the base case. In the base case, you say, okay, we're going to return to 1 and show that the statement is true about 1. And once it's true about 1, because we've set things up in the inductive step, then it's also true about 2. And then it's also true about 3. And then it's also true about 4. And so on and so on and so on. The best argument that I've ever heard to analyze this in kind of a real life picture is like a domino effect. The very first domino is like this one here, and it tumbles over and knocks over the next domino, and knocks over the next domino, and knocks over the next domino. That gives you a summary of what regular induction is all about. Let's get a feel for what we just did in this strong induction. So again, there's all these statements like P sub 1, P sub 2, P sub 3, P sub 4, and so on and so on and so on. Now this time in the inductive step, we did it a little bit different. We showed that 1 and 2 when put together give you 3. So we showed that that implication was true. And then we showed that 2 and 3, when you put that together, you get 4. And so on and so on and so on. When you put 3 and 4 together, you get 5. So when we return to our base case, we needed to show that 1 and 2 were both true to get the ball started. Once that ball is rolling, then we know that P3 is true. Then it's true for 2 and 3, then it's true for 4, and so on and so on.